Welcome back to ECE 501B. Judging from the audience, maybe we just had an exam. I don't know. We did have some of the online students come in during the exam and take the exam with you. It was just easier for everyone, so I appreciate that. Homework number 4. Don't be looking on D2L while I'm lecturing. You won't find it. If you do, let me know. But it's not yet posted. Hopefully it will become posted shortly, and it will be dealing with Chapter 5 material, which is the topic of eigenvalues and eigenvectors, which hinges very much on invariant subspaces. That's really what an eigenvector is. It's an invariant subspace. We'll look at some facts about invariant subspaces. We'll look at the definitions of eigenvalues and eigenvectors, and I may actually post another little video on finding eigenvalues and eigenvectors based on the way that the book is assuming we know eigenvalues and eigenvectors. We really haven't talked about determinants, for example, and finding characteristic equations in the way that you might traditionally do that. And so it's a different way of finding eigenvalues and eigenvectors, and I may just let that be delivered outside of this classroom. Yes? The homework will probably not be due on Friday. I have to look at the dates to see. This is testing season, and I need to find out when our next exam is, just to remind myself and make sure that we're sequencing the homework problems at the appropriate rate. But I don't think I usually like to give you at least one weekend to work on the homework problems, and for that reason I don't think homework 4, or whichever one we're on, won't be due this Friday. Hopefully I won't have to eat my words. I don't think so. So let's remind ourselves of where we have been prior to the exam. We were dealing with Chapter 5, which is dealing with operators. And an operator is a linear map. It's a special linear map, meaning it's going from, or the domain is the same as the codomain in terms of the vector space. You're going from a vector space and mapping back in through a linear map back into that same vector space. That gives us this operator, and we will typically be viewing these operators in a matrix form. And we now have this matrix A times a vector, V, equaling lambda times V, or this linear map is actually taking a direction in the vector space, and if you can think of it that way, and you're mapping back along that same direction. That's the eigenvalue-eigenvector equation. We looked at that for particular matrices. For a diagonal matrix, the eigenvalues are right on the diagonal. For an upper or lower triangular matrix, again, the eigenvalues are there very clearly on the diagonal. For a dense or a non-sparse matrix, it may not be obvious what the eigenvalues are. This particular matrix, I think, had eigenvalues at -1 and -2, just like the previous two matrices. All of these have the same eigenvalues. We then looked at a matrix with no real eigenvalues, which was this matrix -1, 2, -2, -1. And do you remember, if somebody needed to compute the eigenvalues and they said, oh, you're free to pick your field of numbers, could you find eigenvalues for that matrix? Yes, and the field would be the complex numbers. It may not have real eigenvalues, but it does have eigenvalues that live in the complex field. And those particular eigenvalues for this structure of a matrix were at -1 plus and minus J2. But if somebody said, oh, find the real eigen, or maybe you're living on the field of real numbers, then this matrix wouldn't have any eigenvalues. It's only when you allow yourself to enter the field of complex numbers. As we said before, eigenvectors are invariant subspaces. You start on an eigenvector, you map it through that linear map, and you stay on that eigenvector. So those are invariant subspaces, but not all subspaces are invariant. For example, let's think in 3 space and consider the x-axis, the y-axis, and the z-axis. All 3 of those could be considered subspaces in R3. But for this rotation linear map of T, where we are now, if you wanted to just look at the plane and forget we could go up and down in the z direction, this linear map is simply rotating counterclockwise 90 degrees. We are taking the y vector and mapping that down to the negative x-axis. We're taking the component in the x direction and rotating that up on the y-axis. This is just a rotation counterclockwise of 90 degrees. With that linear map, it's not going to necessarily maintain or have invariant subspaces in the real number field. If we now start on the x-axis, let's say we're out at 3, 0, 0 in the R3 space, or in that particular domain, then operating on it with that rotational map, that linear map, maps now from the x-axis up to the y-axis. And for that reason, this y-axis is not a linear multiple, or it's not dependent on the x direction. It's 90 degrees away. So that linear map is not producing an invariant subspace. So not all subspaces are invariant to a particular linear map. Let's now look at this concept of invariant subspaces, or define it, and then move on into some more discussion with maps restricted to particular subspaces. One thing that we should begin with is that these invariant subspaces are pretty special. They don't happen just out of the blue, and they have special properties. And the book is now talking about the idea of actually a restricted operator. This idea of a restricted operator being an operator on the restricted subspace. Is actually very important. So in going back to our earlier example, if we started on the x-axis and our linear map took us back on the x-axis, then that would be the map restricted to that particular invariant subspace, and that would be a restricted subspace. We are going to call a subspace where the behavior, where, maybe I should say, where this behavior is true, meaning we stay on that restricted subspace, we call that an invariant subspace under T. So it has its invariant nature because of this linear map T. And we stay in this restricted subspace. Let's see if we can look at that in a different way. That is, suppose we are given a linear operator T, and that's how we denote a linear operator. We say this linear map belongs to this linear set that has a domain and a codomain that are the same. And let's suppose that we are given U, a subspace of the vector space capital V. Then this subspace U is invariant under T. That's the terminology or the phrase that we will use if you start with a vector in the subspace. Let's say little u belongs to the subspace capital U. Then that implies that the linear map applied to that vector U also lives in the subspace U. And the book actually has developed or uses some notation. They say T essentially restricted to U. And in this case, that restricted operator is an operator on the subspace U. Let's get away from R3 or C3 or these normal vectors, and let's look at a good example from the textbook. And let's start with our vector space V being this guy. What is that? Okay, that's polynomials of degree 7 with the real numbers. That's the field that we're using. So our coefficients are real coefficients, and it's all of these polynomials that are 7th order or less. That's our vector space V. And let's say that our linear map T is the differentiation. We know that T is an operator, or can be viewed as an operator, on V, because if we start with a polynomial that's 7th order and we differentiate it, we'll live or we'll return to that vector space, that collection or that set of polynomials of 7th order or less. Now let's consider a subspace of V to be the set of polynomials that are 4th order or less. And hopefully it's clear that that is a subset, or I'm sorry, a subspace. It's a subset for sure. What do we need it to be in order for it to be a subspace? If U is a subspace of V, what would we have to show? Not that it's a vector space. On the exam, I was looking for a vector space, not that it was a subspace. I wanted it to be a vector space. So there are properties that a vector space has to possess. Here, for a subspace to be, or for a subset to be a subspace, what are the relationships, or what are we thinking? Ask there. Did everybody hear that? It contains the additive identity, and it needs to be closed under addition and scalar multiplication. And U does satisfy those three properties. So it is a subspace of V, which is this set of seventh order polynomials. So U is a subspace, and now let's look at what we have. Suppose we let U be a vector in big U. What can we say about TU? Where does that belong? Does that get mapped back into U, or does that have to be mapped into V, the bigger? So it can go into U, can't it, if we now are saying T is our differentiation map. So that now we can say that P sub 4 of R is in fact an invariant subspace of P sub 7 under that linear map of differentiation. Now I'm sort of giving you some ways of testing your recall or your memory. Here's another quick question. What is another subspace Q of, let's say, P sub 7 of R such that P sub 7 of R is equal to P sub 4 of R plus Q? Can you define a subspace such that when you combine fourth order polynomials? Yes. Pardon? P7 could be Q, couldn't it? Since I didn't do a direct sum, I simply did a sum of subspaces. I didn't do a union or an intersection, I did a sum, so indeed, one solution wasn't the solution I was looking for, that's fine, but a correct solution could be P7, right? Could it be 0? We want the result of the two subspaces combined to be P7. So 0 is a subspace of P7, but it wouldn't be the Q that we're looking for because we want a subspace of P7 such that the combination of that or the sum of that with P4 gives us P7. So you could do, what if we did the following? Maybe if we did say something like a direct sum, if we said, oh, what about A5 Z5 plus A6 Z6 plus A7 Z7, where we can pick those A5s, A6s, and A7s from the field of real numbers. That will also be such a subspace. And that is a subspace. Yes. Oh, we're not doing anything quickly right now except on an exam, right? So I don't know that there is the question was, is there a notation that's maybe a little cleaner than what I just wrote? I think that's pretty clean, actually. It's cleaner in my office, but that's not saying much. But that's not too bad. That just says that these coefficients can be independently and arbitrarily selected out of the reals, and that will then give us a subspace of polynomials that do have powers of 5, 6, or 7. But it also has the 0 vector, doesn't it? A5, A6, and A7 can be 0, all three at the same time. That's why Q is indeed a subspace. Yes?
So for the previous example, what was the point of the illustrated? Why does it matter that four is subspace?
So the question was, can I explain what was going on before? We're trying to understand this concept of something being invariant. And something being invariant, and this is maybe outside the normal eigenvalue, eigenvector thinking, but here we were showing that this, whatever we called it, U, in that example, was an invariant subspace. It was invariant underneath the map, this linear map of differentiation. That's really all we were doing. We were just saying, can you find examples where you have invariance? And here is one such example that's not dealing with things in tall, thin columns, like a vector. Here you have something that's a subspace. It's U, but it's now polynomials, but now with the differentiation map, it's actually an invariant subspace. And that's really that's the only really thing that we were trying to explain or illustrate. And it came from the textbook, so it has to be good, right? All right. Now, let's look at some other facts about invariant subspaces. We're going to start with T being a linear operator. That's a given. And now we can say that the null space of T is invariant. Or I should say, is an invariant subspace. So I'm abbreviating that. We know the null space of T forms a subspace. So that subspace is invariant under this linear map T. If you now know these vectors that are in the null space of T, then that subspace makes up an invariant subspace. Similarly, the range of T is invariant. Wherever we can get to through this map, this linear map T, or this operator T, is in the range. And so if we take a vector, we're in the vector space, and we're going back into that same vector space. We pull a vector from the range, it's going to also be mapped into the range. And the range could be very big. It's not necessarily one-dimensional, as the null space could be big. It doesn't have to be one-dimensional. But what we want to think about, those are sort of extreme invariant subspaces. Here's some more, even more extreme subspaces, which were actually sort of asked about earlier with some questions. Invariant subspaces other than, what do you think I'm saying now? Well, the zero vector is an invariant subspace. That's kind of a benign subspace. Another subspace that's invariant is the whole vector space V. That's a subspace. But we can find other subspaces. For example, if the dimension of V is greater than or equal to 1, and our number field, F, is complex, then we can have other invariant subspaces. Basically, well, we'll get into that in a minute. And B, if the dimension of V is 2 or more, let me say more than 2, because we've already looked at, in the very first part of today's lecture, we saw an example that was a 2 by 2 matrix that did not have any real eigenvalues. So we need to be bigger than 2 if our field of numbers is real. Because you could find a 2 by 2 matrix that does not have any eigenvalues, and we need eigenvalues to even be thinking about eigenvectors or invariant subspaces. So the dimension of V needs to be bigger than 2, and the field of numbers is real. Then we can have some other invariant subspaces. Let's look at starting small. Let's look at studying some one-dimensional invariant subspaces. I'll say studies of 1D invariant subspaces. And really, this is the simplest kind. That's interesting. If we had the zero vector, what's the dimension of the zero vector? 0. So that would be an invariant subspace of dimension 0, and that's kind of uninteresting. So now if we step up one more dimension, now we can have some interesting behavior. So here, let's talk now about a 1D subspace. Suppose we are given U in our vector space and suppose U, a subspace, is now the set AU such that A belongs to our number field, F. Or really what we're saying is U represents all scalar multiples of U. So what happens if U is invariant? So now, if we want U to be invariant, suppose we are given a W that belongs to U. So now W is some linear combination of little u, a vector, some scalar multiplication. Suppose that TW stays in U, or is an element of U. What does that say about TW? More basic than that. So the response was it's an eigenvector, or it's going to give you this eigenvalue-eigenvector relationship, essentially. But TW belonging to U, if we defined U to be this, then we could just repeat what U means. U means it's a scalar multiple of little u. And I don't know that you could tell, but the first U I used was a capital U. The second U was a lowercase u. That was obvious from the context. No, I'm teasing, but please read along, I guess, or hear along in the right manner. So now TW, so far all we are saying is that it's a scalar multiple of W. Which we could write TW then as lambda W, where this lambda, since TW is a scalar multiple of W, then lambda is some scalar in our field of numbers. And if we have such a relationship, TW is equal to lambda W, then we will start to use the terminology that was just used, and we've already been using it already. We call lambda an eigenvalue of this operator T, if there is a non-zero vector W such that TW is equal to lambda W is true. And this vector W is what we've been calling it all along. It's called the eigenvector. But it's actually the eigenvector associated with a particular scalar, and it's associated with this particular lambda. A 1D invariant subspace of T only exists if T has an eigenvalue. So the only way that we will have a one-dimensional invariant subspace of some linear map is if we can find that scalar that satisfies the earlier relationship. TW is equal to lambda W. If we can't find such an eigenvalue, then we do not have a one-dimensional invariant subspace, or we won't have an eigenvector for that particular linear map. Now, what we will be looking at is we can now write this eigenvalue-eigenvector relationship, TW is equal to lambda W, by pulling everything over to the other side. Let's subtract lambda W from both sides and factor out the vector W, and now we can say that T minus lambda I W is equal to 0. Now, we've seen equations like this, some operator times a vector equaling W. Where does that vector live? In the null space of that operator. Thus, and W here is our eigenvector. Thus, the eigenvector of T, again, corresponding to that particular eigenvalue, lambda, or maybe I should say the eigenvectors. We may have multiple eigenvectors. The eigenvectors of T corresponding to lambda are in the null space of T minus lambda I. Now you can see why it was important to learn about null spaces. Now if you can find null spaces, you can find eigenvectors. This also means they are a subspace of V because of what? Because any null space is a vector space. So this also means they are a subspace of V since the null space of any operator is in fact a subspace of V. So now we can think of an invariant subspace, and in particular an invariant one-dimensional subspace, as an invariant direction in our vector space V, and vectors in that direction don't change in direction, don't change direction upon application of this operator T. If we have these invariant subspaces, let's say one-dimensional in this case, then if we apply the operator to those, we stay on those subspaces. Let's look at some examples. Suppose the first example is a linear map that's A times the identity matrix. Now we have T applied to W equaling lambda W. That's our eigenvalue-eigenvector relationship. We want to see what that corresponds to, if we can find a lambda and a W. Well, if we apply T, which is A times I, to W, that's what TW is, and if we say that's equal to lambda W, we can now say that that really just says that AW is equal to lambda W. What's our eigenvalue? A. Our linear map was A times the identity matrix. Those are actually eigenvalues if they're on the diagonal of the matrix, so we sort of knew that already. But how many and what kind of eigenvalues do we have? Do we have any others? If A was 6, is 7 an eigenvalue for this? let's say A is 6, and we have 6, and we're in a three-dimensional space. So we now have 6, 6, ooh, maybe that's the wrong number. So let's use 8. 8, 8, 8 down the diagonal of that matrix. A 3 by 3 matrix. Do we have any other eigenvalues other than 8? No, that's the only eigenvalue we have. So the only eigenvalue in this particular example of t being a times I is just a. So the only eigenvalue is lambda is equal to a. But what are our eigenvectors? What do they look like? How specific did we have to be in picking W? Not at all, did we? It didn't matter what we picked for W. It's just going to get mapped back to W. It'll just get scaled by whatever A was. In our example, 8. So W can be any vector or any direction in this space, and that would correspond to this eigenvalue, the only eigenvalue, A. So this particular linear map of A times the identity has restricted eigenvalues, but it's true for any vector in our vector space V. Or we could say all vectors in V are eigenvectors. Or another way of saying that is the direction. We started out at a 45-degree angle, for example, and we operated on it by AI. We're going to stay on that 45-degree angle. The direction of any vector is left unchanged by application of t equaling AI. Let's look at another example. That one was kind of maybe a trivial example. Suppose now we say, okay, here's T, a linear map on a vector space of dimension 2. W1 and W2 are the coordinates of the vector that operates or is operated on by the linear map. And suppose that that linear map produces minus W2, W1. That's now our linear map. We start with W1, W2, and we map to minus W2, W1. So now let's say W is this vector of two coordinates, W1, W2. If we look at or examine and try to find eigenvalues and eigenvectors for this linear map, let's see what happens. We want TW to be lambda W. What does that mean? Well, TW is just minus W sub 2 W1 by definition of that linear map. So we start with this, and we actually want that to be some scalar multiple, some lambda of the original vector W, so that we want to be lambda times W1, W2. So this is now our eigenvalue, eigenvector relationship, if anything can come out of that, for this particular linear map, T. Now what we want to do is try to find, are there lambdas that satisfy this? And if so, what field of numbers are we living in? And if we can find such eigenvalues, then we can maybe find invariant subspaces. But if we can't find an eigenvalue, we don't have to worry about invariant subspaces. We're not going to have eigenvectors. Is that clear? So let's now look at this and see what we can come up with. Now we can simply equate coordinates. We just have two equations in two unknowns, basically. Well, we have the eigenvalue or the scalar also in there. Let's look at the first coordinate. From the first coordinate, we can now say that minus w sub 2, that's the first coordinate on the left, that should equal lambda w1. Or maybe we want w2 to be some scalar multiple of w1, so let's multiply both sides through by negative 1, so that w2 is minus lambda w1. That's what we obtain from the first coordinate equality or relationship. Let's look at the second coordinate now. From the second coordinate, we see that w1 is equal to lambda w sub 2. But now we have found a relationship or another way of writing w sub 2. We can replace w sub 2 with the right-hand side, which is minus lambda w1. So now we have w1 is equal to lambda w sub 2, lambda w sub 2, but w sub 2 is minus lambda w1. But that's now minus lambda squared w1. Now maybe it's not clear what we have, but if I sort of explicitly put something out there on the left, I have something times w1 is equal to minus lambda squared times w1, and that something is actually just 1. So I have w1 is equal to minus lambda squared w1. That now tells me something about this scalar lambda in terms of its square. I now have minus lambda squared is equal to 1, or lambda squared is equal to minus 1. And now we have some options, maybe. Yes, question? So now the question, where do you want me to, the question was something about w1 being 0. We're trying to find non-trivial vectors. That's correct. So the question was, why can't we just set w sub 1 equal to 0? If we do that here in this eigenvalue-eigenvector relationship, w sub 2 will be forced to 0, and so we'll end up with the trivial 0 vector. But yes, there may be, sometimes you'll have free variables, and then if, let's say you had 5 free variables, we really haven't talked about that here, you might in linear algebra class, but if you had 5 free variables, you start setting those free variables to 1 and everything else to 0 to see what all you can come up with. And that's, I think, sort of what you were suggesting. Let's set one of these variables to 0 and maybe the other one let's find what it's equal to. That one wouldn't have given us any, let's say, non-trivial information. It would have said 0 is equal to 0, which is fine. That's true. But if we want to now see, is there something more that we can find? Here, though, if we restrict our field of numbers to be real, what can we say? We now want a real number when we square it to equal minus 1. It's not happening, is it? So there is no solution for that linear map if we are restricting ourselves to the field of real numbers. Or we're saying no invariant directions. And if we go back to this linear map, what are we doing? We're rotating, aren't we? We're taking the y position and going into minus x, and we're taking the x position and going into y. So again, this is a 90-degree counterclockwise rotation. And no vector that you start with and you rotate at 90 degrees is going to stay in the original direction. That's really what this is saying. If we're dealing with real numbers for our scalar coordinates in these vectors. So no invariant directions, and that was maybe clear if we would have just looked at this being rotations in R2 by 90 degrees. And a rotation is not preserving direction. But now if we look at a different case, suppose we now look at our our field of numbers being complex. Now we say lambda squared is equal to minus 1. Now since we're in ECE 501b, we have plus or minus j, which is plus or minus the square root of minus 1. Those are our two possible eigenvalues that satisfy lambda squared equal to minus 1. Now, let's see what we can do for eigenvectors. And eigenvectors, we need to find eigenvectors all based on or being associated with specific eigenvalues. And now we have two eigenvalues. For this eigenvector, the first one, let's look at lambda equaling j. So now we have minus w sub 2, w1, that's tw, equaling lambda w, and we said that that needs to be j, w1, w sub 2. Am I that soft? I'm almost running out of battery power, but maybe I need to crank up the volume. Keep the door closed. Kind of a interesting comment or concept. Louder keeps the door closed. Never mind. Where were we? Minus w2, w1 is j omega 1, omega 2. This now, if we look at equating coefficient or coordinates, we now have minus omega sub 2 is j omega 1. Or we could say now that omega sub 2 is minus j omega 1. So whatever we pick for omega 1, that's living in this field of complex numbers. We now need to force w sub 2, the second coordinate, to be minus j, or minus square root of 1, times whatever we pick for w1. So now we have the eigenvector, let's say associated with lambda equal to j, and that eigenvector now is w equaling w1 minus j w1 with w1 belonging to the complex field. Meaning if we pick W1 to be 1, then the second coordinate would just be minus j for an eigenvalue of j, positive j. What about the other eigenvalue and its associated eigenvector? Well, the door closed, and now look what happened. What do you think's going to happen besides everything's going to die? Let me just assume we'll be okay. Uh-oh. Poor assumption. So I will keep talking and see what is causing my problem. But what do you think's going to happen with the other eigenvalue, its eigenvector? So do you know how to find it? That's the main thing. You may not be able to determine it right away, but the main thing is, do you understand the strategy that we're using? Whoa, sorry. Now we'll have to rotate. I'm illustrating some of these rotations. This is not real. Okay? This is not real. This is the imaginary space that we're playing in. Yeah, so the computer happened to just illustrate. What did it? Pardon? It got excited, that's right. We excited that particular eigenvalue. Let's excite the other one. So now if we look at the other case, the other eigenvalue, and try to find its eigenvector, we have minus w sub 2 w1 is now equal to minus j w1 w2. Using the strategy that we just did, we now have minus w sub 2 is equal to minus j w1, or we could say now that w sub 2 is equal to j w1. And now the eigenvector associated with lambda equal to minus j is this eigenvector w of w1 j w1, with w1 being a complex number. And that should have been completely obvious from the rotating screen. Or maybe you'll never forget that particular concept. Let's now get into, I'm going to skip over the brute force way of finding these. We sort of went through an example of that in 2 dimensions. Then I'll talk more about that in an additional lecture. So I'll make that a lecture that follows this one. But let's get into some theorems associated with these concepts of eigenvalues and eigenvectors. Let's look at theorem 6 in chapter 5. This particular theorem says that the eigenvectors associated with distinct eigenvalues of the linear map T, or the linear operator T, are in fact linearly independent. Do we get what that's saying? If you now have a linear map, and let's say its eigenvectors are 1, 2, 3. We have 3 eigenvalues, and they are distinct. That means each of the eigenvectors, the eigenvector associated with 1, the eigenvector associated with 2, and the eigenvector associated with 3, if we find those 3 eigenvectors, they will be linearly independent. That's what this theorem is saying. So if you have distinct eigenvalues, that's giving you pretty nice properties relative to these eigenvectors. That's really what this theorem is telling us. Let's look at a proof of this. Now, you thought your head was spinning earlier. Let's see if we can go through this particular proof. First, let's start with T being this operator on a vector space V, and let's establish some notation. Let's say that we now have, maybe I need to pick a different team. Michigan's not doing so well, but little m is how many eigenvalues, let's say, that we have, and they are distinct. So let's now say that we have m, little m, or Michigan, distinct eigenvalues. And let's now assign the associated eigenvectors, v sub 1 through v sub m, with those eigenvalues. And just to keep track of things, although it really wasn't stated in the theorem, I don't believe, was it? No. The size of our linear map, or the dimension of our vector space, we're assuming it's Nevada. M can be less than or equal to the dimension of our vector space. So M is less than or equal to N, where this is now, let's just go ahead and define that to be the dimension of our vector space V. And in fact, we're going to prove this by contradiction, which, how do we do that? We're doing a proof by contradiction, and we have statement A and statement B. Let's say in the statement, or in the theorem, statement A implies statement B. Now, if we want to do a proof by contradiction, what are we trying, or what's the approach? We negate the B, don't we? We say not B, and we look for a contradiction. And we can assume that statement A is true. All right, so now let's assume now, what are we saying? We, in the theorem, are basically, we assumed that our eigenvectors were linearly independent. Let's now assume those eigenvectors are linearly dependent. That's negating the last statement, or statement B. So now assume V1, V2, V sub m, that set of, or that list, is linearly dependent. And what does that mean? That means that of those vectors, at least one of those is a linear combination of the others, or in the span of all of the others. So this means at least one is in the span of the other vectors. Now let's just introduce some notation. Let's let L be the smallest integer such that V sub L, that L vector, is now in the span of V1, V2, v sub L minus 1. So we're looking at these vectors, and we pick vector 1, and we go, is this in the span? And it's not. Then we say, let's look at vector 2. That's not in the span of v1 and well, it's not in the span of v1. v3 is not in the span of v1 and v2. We finally get up to L, and it's now contained or dependent on the previous L minus 1 vectors. That's all that we're saying. And L is the smallest integer where that's true. And maybe it's 2 or 3. Let's make it 5. Okay, so now it's 5 if I need to refer to it. So now we have v sub L. That means we can write v sub L as a linear combination of the previous 4 vectors. We now have a1 v1 plus a sub 2 v2 plus up to a sub L minus 1, v sub L minus 1. Now, let's apply our linear map to that vector v sub L. And again, these v's are all eigenvectors. So let's now apply the linear map T to both sides of this expression for v sub L. Now we have T v sub L is equal to, and a1 through a sub L minus 1 are scalars, so this is a1 T v1 plus a sub 2 T v sub 2 on up to a sub L minus 1 T v sub L minus 1. And what's the left-hand side? T v sub L, if v sub L is an eigenvector, this is now lambda sub L v sub L. By definition of v sub L, it had eigenvalue lambda sub L. And likewise for what's on the right-hand side, we have a1 times lambda 1 v1 plus a sub 2 lambda sub 2 v2. These are all eigenvalue eigenvector pairs, plus a sub L minus 1 lambda sub L minus 1 v sub L minus 1. And I may want to refer to that. Let me call that equation 1. But this equation was true since T v sub I was equal to lambda sub I v sub I. Where these v sub i's were eigenvectors. But remember what v sub L was. V sub L was a dependent eigenvector. So v sub L was this a1 v1 plus a sub 2 v2 plus a sub L minus 1 v sub L minus 1. If I multiply that equation on both sides by lambda sub L, I'm going to get on the left the same value, and then I'm going to be able to combine these two equations. That's my motivation for doing this. In this blue equation, let me multiply that all terms by lambda sub L. So that now I have lambda sub L v sub L is equal to a1 lambda sub L v1 plus a sub 2 lambda sub L v sub 2 a sub L minus 1 lambda sub L v sub L minus 1. All I've done here is just multiply by lambda sub L, both sides. I can do that. And let me call this equation 2. And if I now combine equation 1 and equation 2, if I subtract them, I think you can see that the left is at least 0. the left-hand side. And now I'm simply going to be taking lambda sub L's away from lambda 1, lambda 2, etc., because all those other terms are the same. So now I'm just subtracting the lambdas and lambda sub L from each other. So let me now combine one and 2. So on the left I get 0, and on the right I have A1, lambda 1 minus lambda sub L V1, plus A sub 2, lambda sub 2 minus lambda sub L V2, plus, and I can just keep going until I get A sub L minus 1, lambda sub L minus 1, minus lambda sub L V sub L minus 1. And I may refer to that as 3. But remember how we picked V sub L. That was the very first vector that was dependent on all the others. So that means that these vectors, V1, V2, V sub L minus 1, are linearly independent. If we have a combination of linearly independent vectors that equal 0, what's the only way that can happen? All those coefficients need to be 0, don't they? And the only way these coefficients can be 0 is if all our A's are 0, or if we have lambda 1 as lambda sub L, lambda 2 as lambda sub L, and if we have lambda 1 equal to lambda sub L, that means they're the same, right? And we assumed they were distinct. So there's our contradiction. That's where we're going. I'm not sure we're going to have time, but is that clear? Let me try to write that down. Question? So now right. So now we're assuming, well, you're assuming that the first vector is some direction, and now what you want to do is 2 in the same direction as 1. Is that the smallest vector? So 2 is really as big as you can, or small as you can have L. Now, I'm going to try to write down what I just tried to describe, because V sub L was the first vector that could be written in terms of the earlier vectors the list V sub 1, V sub 2, up to V sub L minus 1 must be linearly independent. And now, after studying for the exam, you know what that means. You know that if we have equation 3 then, equation 3 was that this combination, this linear combination of linearly independent vectors was equal to 0. Equation 3 implies all the coefficients are 0, or i.e. A sub 1 lambda 1 minus lambda sub L is equal to 0, etc. And therefore, we have one of two possibilities. Either there are non-distinct eigenvalues, meaning all of those lambdas, lambda 1 is equal to lambda sub L, lambda sub 2 is equal to lambda sub L. That gives us a contradiction. Or case 2 is all the a sub j's are 0. But we picked our a sub j's to create v sub l in particular. V sub l was equal to a1 v1 plus a sub 2 v2. And if we now have that, all of those a's being 0, then v was equal to 0, and that's a contradiction. We wanted that to be in our original list, which was some non-zero. So let me conclude saying, but v sub l was that linear combination would imply v sub l is equal to 0, which is a contradiction. So either option for those two pieces of our coefficients being 0 leads to a contradiction, which now says that therefore this original set of vectors that were associated with distinct eigenvalues, v1 through v sub, Michigan, v sub m, must be linearly independent. And that's the nice thing that we wanted to be able to show, that if we start with distinct, or if we find distinct eigenvalues for a linear map for an operator, the eigenvectors associated with those distinct eigenvalues will be linearly independent. And that will allow us to make nice comments or nice results. We'll pick up with more corollaries and theorems in Chapter 5 later.